Welcome to iCANX Talks, Connecting the World and the Universe. My name is Professor Martin Thuo, coming to you from North Carolina State University on the eastern coast of the United States. Today, we are very privileged to have Professor Andrea Ferrari from University of Cambridge, and the panel will consist of myself, Alice, and Julia Chang is going to be our challenger. A little bit about our guest today. We're very privileged to have Professor Andrea Ferrari, who is a professor of nanotechnology at the University of Cambridge and a fellow of the Pembroke College. He founded and directs the Cambridge Graphene Center and the EPSRC Center for Doctoral Training in Graphene Technology. He chairs the management panel and is the Science and Technology Officer of the European Graphene Flagship. He is a fellow of the Royal Academy of Engineering, the APS, the MRS, the Institute of Physics, among many others. He has received many awards, and Professor Ferrari, I'm not going to go through all of them. I don't want to take over your time. But he, very specifically, I want to highlight the Royal Society Brian Masser Award for Innovation, the Royal Society Wolfson Research Merit Award, the Marie Curie Excellence Award, the Philip Leverhulme Prize, and the EU 40 Material Prize. Today, Professor Ferrari is going to be talking about to us about layered materials, and I welcome you to share your slides. Professor Ferrari, the stage is yours. Thank you.
Okay, good afternoon. Can you hear me?
Yep.
Okay, thank you. Yes, something has changed in the settings when I was sharing now, so hopefully you will be able to see the video. Otherwise, we'll need to try again later. So it's a great pleasure today to cover the topics of layered materials and discussing about the production, the application, and some of the different areas where these materials are used. Let me start by saying that, as I mentioned, I will try to discuss different ways of having mass productions of these technologies and materials. And then I will discuss more specifically in the second part of the talk about the optical properties, the application in modulators, in photodetectors, in lasers, and in quantum devices, if there is time. So just to remind ourselves what was the situation a long time ago. So if we go back to 2004, it was really a very tiny sample what could be produced in the case of graphene just by exfoliation. As you can see here from this picture, we are talking about a very tiny dimensions of a few microns, and then it took in the space of a few years, just in 2010, thanks to the work of Texas Instruments and of SKKU in Korea and Samsung in Korea. So Texas Instruments and University of Texas in 2009, they were able to grow 1 centimeter square of graphene, and the following year, using the same recipe, 30-inch was grown. So in the space of just 6 years, we went from a tiny sample of a few microns to 30-inch large-scale production of a material, and that is certainly a significant feat. Nowadays, in 2023, things have gone forward, and a few years ago, one Cambridge company called Einstein, actually Einstein is a German company, but they acquired a spin-off of the University of Cambridge called Einstein, and they started producing a system that was called the BM Pro. Is a CVD system that was able to produce wafers of 4 to 6 inches of graphene. And this was then improved to produce 300 millimeter wafers. in the so-called BM300T, or a roll-to-roll production of continuous graphene in the so-called Newton system. So in this Newton system, there is a roll that goes from the top to the bottom, and the graphene is attached to or produced on the copper foil in a continuous manner. So if we look at the throughput of this system, we can see that just a single BM303 can produce 1,000 or 2,000 square meters a year of material. And if we look at the Newton system, a single system can produce 10 to 20,000 square meters a year of material. So this is really a very large amount of material in a single system for production. And of course, you can buy as many as you want of them. And also the cost per square meter is massively decreasing. And we are going to approach soon the 10, 20 euros per square meter. The Newton already can produce graphene at the cost of 60 euro per square meter. I now have a video. Let's see if you can see. So this is the 4-inch system, the small system of Einstein. And now we are going to look at the BM300. And you can see the silicon enters into the chamber and then it's covered continuously by the graphene. And everything is computer controlled and you can get a wafer scale samples. And finally, a look at the Newton. The system grows graphene from the top to the bottom. Okay, you can stop here. And the next generation system is what is called the CCS 2D system. And you can see it here. And this is a closed-coupled showerhead system, is a metal organic CVD system. And this system is able to grow not just graphene, but also MOS2, HBN, all the transition metal dechalcogenides, and can also grow them in heterostructures directly. I will skip the video and then go to a different topic. So that's the growth of these materials by CVD techniques. There is another approach that was also pioneered many years ago, the so-called liquid phase exfoliation. So in the liquid phase exfoliation approach, you take a chunk of graphite, you may want to throw it in some solvent, and then shake or sonicate, and then eventually you will get 100% monolayer flakes. This was pioneered at Trinity College, Dublin, in collaboration with us in Cambridge in 2008. So what happened is that when we tried to do this, we were successful, but the yield was very small, but still bigger than zero. So it was 0.8% yield. And that was in 2008. It took over 10 years, up to 2017, 18, in order to develop this new system that you can see here, the high pressure homogenization system. And in this system, you push the graphite to an interaction chamber, and this exfoliates the graphite flakes, and then you continue going on and off in a cycle. And this is able to produce very large amounts of materials. A simple system of a few centimeters, like 1 meter times 1 meter, can produce almost 5,000 liters per year of ink. So once we had graphene on ink, we could do printing. You can see an inkjet printer of the food of the graphene, printing the name of the University of Cambridge, for example. So this started off a new era of research of printed electronics based on graphene and related materials, and so devices such as LEDs, displays, or communication antennas for RFIDs, or energy storage systems, or sensors, and printed circuit boards, and smart textiles, and so on. All of these were produced over the years by applying these simple printing techniques, different types of printing techniques, from inkjet to gravura to flexo and so on and so forth. So here we can see an example of a printed device where we take our ink and have a circuit board that is on the screen, and then you simply push the graphene on the top of the design, and then you get immediately a printed device after that. So this is an example of, again, work done in collaboration with a company called Novalia in Cambridge. We have a piece of paper. This is normal paper. We have sensors. We have conductive lines and so on. And all of this is done by using graphene. So on the top of it, we can put a picture. Like you can see here, there's a picture of different types of musical instruments. And then if we look at the video, so you probably, hopefully you can hear the sound. Each instrument is making a different sound. So we have a piece of paper with printed devices on the top, and then these devices can be played. And this is a very cheap technology that is enabled by graphene. Another approach is not the one of 2D printing, is the one of 3D printing. And again, this one was developed over several years. And this is an extrusion system to print graphene-based filaments. And then they can go in a 3D printing system, and you can print shapes and different types of things as you want. Within the graphene flagship, there are many industrial partners working on graphene-based composites and technologies. For example, Avanzare, where they create additives for industrial scale resins. Another example is Cambridge Graphene of Versarian, that they produce graphene inks and composites, and capacity is massively increased to several tons of production a year. And these are examples of devices made like the skeletons, headsets, and so on and so forth. In Italy, for example, there's a company called Bidimensional, and they also are using graphene composites for different applications. And this is one of the first examples that they did, this Momo design helmet where graphene polymer composites were used. And again, other companies and the University of Manchester, Lancaster, they produced drones to test the graphene polymer composites for aerospace application. Still in this area, we have been working for several years with Airbus within the graphene flagship. And one of the projects is concerning the tail of the A350, where there are dispersions of graphene and related materials into carbon fiber mats. And these have been tested for this application, as you can see here, in collaboration with the Italian Research Council. So the ability of having inks of different types really opens up a variety of opportunity in this field. Another area that is of great interest is the area of space applications. And again, this was a result of collaborations within the graphene flagship, in particular with a company called Leonardo in Italy, ULB in Brussels, and the CNR in Italy, and of course with the support also of the European Space Agency. So there are many opportunities for graphene use in space. I will now give some examples. The first example that we look at is the problem of how we remove heat from one part of the satellite. So when the satellite is in the space, one part of it is subject to heating from the sun. The other part is exposed to the open space, so it is extremely cold. So we have the necessity to move the heat from the hot to the cold part. And of course, the traditional way of moving heat or cooling is to use like pumps, as we do on Earth, for example, with air conditioning systems. However, if you have pump, you have moving part, and that is not good for space applications. So you would like to have a device that does not have any moving part. And this has been done by using the so-called loop-it pipes. And the loop-it pipes are basically some metal wicks is a porous metal system that generates a capillary pressure that allows to evaporate a liquid, and then the vapor will then saturate and condense, and then it will be heated again on the other side. And all of this will create a circulation, and so we'll remove the heat from one side and bring the cold to the other side. And it does not require any moving parts. So why graphene is interesting for this? It increases the wettability, and so it reduces the startup time. The startup time is very important because, again, for the same reason, there is no pump, there is no moving part, so there is no switch to switch these pumps on and off. They have to self-start, and they self-start when the heat on one side is enough for this to work. And so some of the applications in space have had troubles because they could not be started. The other point is the layering that allows the preferred liquid stream to take place, and increased wet thermal conductivity helps transfer the heat from the source outside the steel shell to the capillary pump. And then the presence of graphene also reduces the pore size of the metal wick, so it increases the capillary pressure. So these are this is a picture of the device, of the entire test system, with the condenser, the liquid reservoir, the evaporator, and with the graphene coated wick that is at the inside. And this was then tested by doing zero gravity flight campaigns like this one. This is actually the picture from the plane, and this is me that trying to move in zero gravity, which is not very easy to do if you've never done it before. However, in the rest of the plane, people are doing experiments, and this is actually what is done during this test, and that allows the test to be done not just in zero gravity but also in 2G. And the tests were very positive, and the results showed up to 800% improvement of performance. Another set of experiments, again collaboration and led by the University Libre de Bruxelles, is the test of how do we print, or how do the liquid behave in space. So advanced research on liquid evaporation in space. One of the ideas could be that in a long-term space mission, you could bring a bottle of graphene or some material like that, and then if you need a new components, you would just use a printer like on Earth in order to print them. But of course, gravity is fundamental to print, so there are lots of questions that need to be answered. So already 3 or 4 years ago, actually even more than that, probably 4 or 5 years ago, we started this work, and this led to a first launch in Sweden. In the north of Sweden, there is the European Space Range, is in the north, 200 miles north of the Arctic Circle. So you can see here at the bottom of the rocket, and this is the launch building. And we also have done an experiment recently, last year during the winter, and the winter is very nice at the Arctic Circle because you can see the northern lights, as you can see in this picture here that I took. I never saw them before then. That's the picture of the other rocket. You can probably barely see is with an M15, so the Maser number 15. The other one was the 14th. And of course, everybody's dressed up for the cold. So this is the new launch pad, and you can see probably here the launch on the right. It takes a few seconds.
Minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
And there is a second stage of the rocket that gets separated while this is going to atmosphere. And this is another picture from the summer experiments. You will see now. And the rocket goes into the atmosphere, and then it deploys a second stage and a balancing system. and this allows it to be very stable, no rotations anymore during the experiments. Okay, you can see the Earth here now. Okay, so it then comes down and you will collect the experiment. More recently, again, this collaboration has continued, tackling another interesting question, is the production of the new environments for astronauts on the moon. And the moon is now very interesting because of the planned missions to bring habitats there in the next few years. For example, the NASA Artemis mission. This little rover was designed to have experiments on the wheels, as you can see here, and the wheels will interact with the surface of the moon, and the surface of the moon is full of dust that is called regolith. And this is very different from the dust that you can find on Earth, because it's very sharp, it's very damaging. It can damage all sorts of equipment, and it can enter into the electronic systems and so on. So together with the Emirati Space Agency, the European Space Agency, and with the collaboration with many institutions, including Fraunhofer, MIT, and so on, we have been working on this rover for about 4 years. And then, as you can see here, in December 2009, there was a launch of the Falcon X rocket.
5, 4, 3, 2, 1, ignition. Stop.
And this rocket launched the spacecraft towards the moon. And then it took a low energy trajectory. So it went to up to 1.5 million kilometers and then come back by gravity in order to save fuel and do a sort of let's say, a user-friendly trajectory towards the moon. In April 2023, the rocket went in lunar orbit. And on the 25th of April 2023, it was supposed to land, the lander of the spacecraft was supposed to land. And this is a picture that was taken just before landing. You can see the surface of the moon, you can see the Earth, and also this black stuff at the back is not like a hole, of course, it's just the shadow of the moon on the top of the Earth. And then it was the rocket was approaching the rover, and the lander was approaching the surface, but then it crashed on the lunar surface. And this is the control room, and people were not very happy at all. It was kind of disappointing. So the lander may have miscalculated the attitude, and then it unfortunately crashed on the surface of the moon. So the experiments planned could not take place, but it was a very interesting learning curve for everybody, and we will maybe try again in the future. In any case, there is no fuel, there's no atmosphere, so the graphene is still there. So when in, I don't know, 20 or 30 years' time, somebody will go there to look for it, that there will be sort of lunar archaeology. They will find our samples, and maybe we can measure them at the time. Other experiments that can be done are on the International Space Station, and there are also many other opportunities, but I don't want to continue on this topic. I want to move on. So just to say that there is really a lot of opportunities for research relative to space application, and in particular, materials for space application are becoming very central. Now, the development of technologies is coincided always with industrial revolutions. So we are familiar with the first and second industrial revolution, the advent of machines and so on. And then a few years ago, the fourth industrial revolution was the cyber physical system, the sort of Internet of Things. But what is happening now is the fifth industrial revolution, where artificial intelligence will be intrinsically connected with devices and, of course, with global connectivity. In fact, somebody calls this the Industry X.0, the new evolution of technologies, where many different technologies and innovation, cyber physical production, smart devices, and so on and so forth will all come together with artificial intelligence. In fact, if we look at the data communication, the global world mobile world data traffic has been massively increasing over the years. And if we just look at the past few years, it went from 38 exabytes, so an exabyte is 10 to the 18 byte in 2019 to an expected 160 in 2025. So in fact, if we look at the average speeds of mobile phones, we see that when 4G came out, it seemed a big deal with respect to 3G, and it was a big deal with respect to 3G. But in fact, the huge increase is being generated by the advent of 5G. So the 5G antennas, they now need to process an enormous amount of data compared to what was happening with 3 and 4G. So now the bottleneck becomes the intra-data center optical transceivers. They need to migrate from 400 gigabit per second to 1600. In fact, they now need to migrate to 3200 gigabit per second at a lower cost per gigabit. And if we look, the digital devices require more bandwidth. The optical connectivity has to improve in order to satisfy the needs. And the needs are driven by the digitalization, energy, sector, and health, the cloud computing, the IoT, the 5G, the 6G, the high-performance computing, all connected with the artificial intelligence. So in fact, the 6G will be a convergence of 5G, AI, data analytics, and Internet of Things. So this high-performance, low-latency computing will bring the AI to the cognitive level. And the solution for all of this is photonics, because the photonics is the key technology that will allow clusters of processors and memories to interact together with unprecedented efficiency and low latency, and power and energy consumption. We cannot discard the sustainability challenges. 1 hour of Zoom call can easily produce 300 grams of CO2. Training of AI model can be corresponding to the 5 times the energy that a car is using. And worst of all, the energy required to obtain 1 Bitcoin to do that data mining can be equivalent to the average energy used by 1 American family over a period of 2 years. So we really need to find new technologies with low energy consumption. Already now, the IT is accounting for almost 4% of the global emission. And by 2040, this can go up to probably 20%. So the challenge will not be planes, because those are basically saturated. The challenge is the increase in the needs driven by the ginormous data traffic, driven by the development of AI, by the use of the internet and so on, will shift a lot of global emission to the electronic devices, photonic devices, data communication devices. So the mission is, how do we change the architecture in order to massively decrease the energy consumption? So the question is, how do we get more out of Moore's law? And quite interestingly, if you go to the original paper of Gordon Moore, there is a couple of sentences in it that says, it may prove to be more economical to build larger systems out of smaller functions, which are separately packaged and interconnected. So he recognized that at the end, you cannot continue with the scaling law. So instead of making devices smaller and smaller and smaller, but just use bigger ones, but interconnected. So the idea is to split the functionality into multiple chiplets in a multi-chip package, and then design disaggregated computing systems. And this has then requires a lot of input in terms of photonics, because we need fast transmission and low power. However, if we look at a chip-to-chip ultra-fast optical links, when we use copper wires for an increasing frequency, we have that the losses are becoming too large. So the losses are so big that it's becoming ineffective to do so. So in order to reach this co-packaged electronics photonics, the solution has to be using some materials which have low losses. And then, of course, the proposition here is that graphene and related materials are the solution to overcome all these problems of the data center, the 5G, the 6G, the interconnection, because already by 2025, the technology based on graphene can reduce by 75% the cost, by 75% the power consumption, while at the same time making quicker devices and with other capacity. So all of this is predicated on many properties. For example, the fact that you don't need cooling, you can work at different temperatures, but also the fact that graphene is wavelength agnostic. So it really can work with any wavelength at the same time. And this is really a unique capability of the material. So why is this? So if we look at the band structure of graphene, there is no cutoff wavelength and the absorption is broadband. So the optical absorption is governed by interband and intraband transition. This is what is called the Dirac cone. The Dirac cone is actually the reason why the Nobel Prize on graphene was given. It was not for the Scotch tape, of course. It was for the fundamental physics related to the electrons and holes that are called the massless Dirac fermions. So I'm not going into the details of the physics, but just to say the beauty of all of this, that the very reason, the very core of the reason why graphene was awarded a Nobel Prize is providing the new physics that is fundamental for the future of communication. So in the simplest possible manner, if I have a graphene with a band structure with a certain doping, if our energy is bigger than the doping, I can create an electron hole pair, so I can have absorption. If it's smaller, I cannot, so I have Pauli blocking and the signal goes through. This will be the simplified view of how things work. Unfortunately, there are other transitions that are happening intraband. These are always happening. We cannot get rid of them. And so these are actually where all the research is going on now in order to minimize this absorption. So if we look at the graphene absorption, we are not going to discuss terahertz today. So if we focus on the larger energy range, we have a flat 2.3%, and that this should go down to 0, but it doesn't go to 0 because of intraband transitions. So all of this can be described by this Kubo formula that looks complicated, but is actually super simple because it's only terms that we know, like tangent, arctangent, logarithm, and so on. And all the other terms are known, are pi's and the speed of light. The key physical parameters are the temperature, the Fermi level, so the doping, and in particular this tau, this scattering time, that essentially is telling you how bad or how good your sample is. So in a very simplistic way, not fully correct, but good to get an idea, the mobility of your device is inversely proportional to the doping and directly proportional to the scattering time. So the longer scattering time, the better is your material. So if we consider 3 times of 10, 100, and 300 femtosecond, this corresponds to 200, 2,000, and 6,000 centimeters square volt per second in terms of mobility. So 10 femtosecond is really a very bad piece of graphene of many, many years ago. 100 femtosecond is a reasonably good piece of graphene that anybody can get nowadays. 300 plus femtosecond is what people are trying to achieve at the moment. Of course, we're not speaking about low temperature measurement on flake exfoliated by Scotch tape. We are actually looking at large area graphene grown on a wafer scale. And so if we go further, we look at the dielectric function, as if the real part is not changing too much as a function of the scattering time, but the imaginary part, which is basically everything that rules the modulation, massively changes according to the scattering time, as we expect. So in order to modulate light, the simplest approach is to take a piece of graphene and put it on a waveguide, or 2 layers of graphene on the top of the waveguide. They behave as a capacitor. When this capacitor is charged, the carriers accumulated on the top of the waveguide, and so change the absorption, the effective index of the waveguide. When the capacitor is charged, the waveguide is transparent, so there are no extra losses. So that explains why graphene is an excellent candidate for loss reduction. So both modulators and detectors in graphene can then be placed on top of transparent waveguides with negligible extra losses. So if we now compare the silicon photonics with graphene plus silicon photonics, so it's not silicon photonics with graphene photonics. No, the idea is that we are going to marry graphene with silicon photonics. So instead of an active photonic circuit, we can use, in the case of graphene, a passive one. In the silicon photonics, we have these free carrier losses that are really a problem. In graphene, we can work in the optical transparency. We don't need the carrier losses. In the silicon photonics, we have static power consumption. Instead, the capacity modulation that we use if you use graphene plus silicon photonics makes so that there is no power consumption when I'm transmitting, let's say, the 1 and the zeros, but there is only power consumption during the transition between 1 and the 0. So that's why we cut off 75% of the power consumption. Of course, silicon is not interacting with light properly, so we need implantation and germanium epitaxy. But in the case of graphene plus silicon photonics, we don't need an implantation or epitaxy. So then there is the final thing, the integration with lasers, that is typically done with hybrid 3-5 light sources. The integration of graphene plus silicon photonics with laser could in principle be done with integrated light sources with layered materials. However, this is not yet functioning at the moment, so the last bit is still going to be heterogeneous integration. So now graphene photonics can then be integrated on passive optical circuits, so it can be compatible with different types of platforms, silicon, silicon nitride, glass, and so on. It offers intrinsic broadband operation, high-speed amplitude and phase modulation, ultra-speed, high-speed for photodetection, and it is very efficient in terms of thermal properties. So this graphene-based integrated photonics will extend the capabilities, not replace, extend the capabilities of silicon photonics integrated circuits by planar integration. And the main application will be high-speed optical data communication to meet the increasing demand for bandwidth. So we have the laser. As I said, we are not going to replace the laser with graphene for the time being. However, the modulator, and then graphene offers both electroabsorption and electrorefraction modulation, and electro-optical index change quite significant. And then photodetection, graphene works at high speed, broadband, and is platform independent, and it doesn't require any germanium epitaxy. So let's now look at some examples. For example, looking at the optical modulator, the very simplest approach for optical modulator is to have this single layer graphene capacitor, one single layer of graphene on the top of a waveguide. That's enough. However, what happens, as mentioned before, the silicon is doped, so silicon has losses. So if we put only one layer of graphene on the top of silicon, yes, we do have modulation, but look at this, between 100 and 300 femtosecond, there's basically no difference because everything is limited by the silicon substrate. So that is why we have this double single layer graphene on silicon approach. This is the most common at the moment. Everybody's working on this. And it's not a double layer of graphene, it's a double single layer of graphene. What does it mean? It means that we have two individual single layers of graphene separated by a dielectric layer. And this capacitor is now shielding the functioning of the modulator from the silicon doping, and that's what we get. We get a very good modulation of the absorption, and of course, consider this is a logarithmic scale, a significant improvement of performance when we go from 10 femtoseconds, so from bad graphene, to 100 decent graphene, to 300 very good graphene, and maybe to 1 picosecond extremely good graphene. So in the two cases, if we use only a single layer, we need a doped silicon waveguide. There are background losses due to silicon free carriers, but it still has good modulation efficiency. In the double single layer, it works for any passive waveguide. There is a background loss due to the graphene mobility only, so not the one due to the free carriers. So we are now limited by the graphene itself, not by the substrate, and there is a very large modulation efficiency. So let me skip this slide and let's go to the next one. So in 2018, we realized together with CNIT and IMEC and others the first graphene phase modulators, at the time working only at 10 gigabit per second, but this was the first demonstrator. It was transmitted over 30 kilometers or 20 kilometers of single mode fibers, still at 10 gigabit per second. Afterwards, using compensation of the due to the positive chirp that graphene allows, the transmission was done up to 100 kilometers of single mode fibers at 10 gigabit per second. And a few years ago, together with IMEC, Nokia, and Ericsson and CNIT, we produced this fiber-based link modulator working at over 100 gigabit per second. These are examples of graphene double single layer on silicon nitride waveguides. On the left, we have electro-absorption modulator. On the right is the phase modulator. I'm not going to go into the details. I'm just going to show examples at the high level. So this is a 120 micron electro-absorption modulator on silicon nitride working at 25 gigabit per second. And then we can put graphene double single layer modulators on silicon insulator waveguides, and in this case working at 50 gigabit per second. The fact is that now we are approaching the 100 gigabit per second, and the frequency is well above 30 gigahertz, is almost 100 gigahertz as well, about 70 gigahertz. So things are really moving very quickly. And this is, for example, a combination of an example of a Max Zehnder modulator based on double single layer graphene. There is this figure made called VPIL. I'm not going to go into the details, just to say that commercial 3.5 CMOS capacitors or CSCAPs have a VPIL around 0.1, 0.2, and the first ever attempt done with graphene is already 0.2, already matching the state of the art. Together with CNIT and IIT, we have then demonstrated in 2021 the first wafer scale integration. So this is 12,000 modulators that have been directly fabricated on wafer using graphene growth and transfer at the large area, working at a decent 20 gigabit per second. And you can probably see here, if you look at the contrast, there are some regions of darker contrast, and these are the pieces of graphene, and they are all they're all crystals of graphene grown in an array, so it's much easier to put them down and integrate it into devices. In the UK, a collaboration between Cornerstone and the Graphene Center has launched the so-called Layered Materials Research Foundry. So this is a foundry provider for wafer scale up to 8-inch wafer photonic integrated silicon and layered material devices. We are now setting up the facilities. There will be some test runs, and this will be go public in the next couple of years. But this is already a first test run with several modulators on a large 8-inch wafer. We now consider the second ingredient, after the modulators, are the photodetectors. So there are different ways of detecting light with graphene. One is based on the photovoltaic effect. The other one is the photothermoelectric effect. The other one is the bolometric effect. The other one is called the Dyakonov-Shur. I'm not going to discuss all the examples. I'm going to focus on the photothermoelectric effect. The photothermoelectric effect is good because it allows direct photovoltaic generation, is bias-free, there are no dark currents, is high speed and broadband. So, and is all based on the modulation of the Seebeck coefficient and the change in the electronic temperature across a junction. So in order to create these devices, you need to create a PN junction, a double junction in graphene, and this is one of the schemes in which was done, probably easier here. So we have a split gate, and the split gate allows you to change from P to N, the doping of graphene next to each other, and that creates the modulation of Seebeck coefficient that we need. So without going too much into the details, just to show that the results, the device works, the responsivity is quite decent, and at the time of this result was the highest for any single layer graphene CVD Of course, we are always considering large area fabrication, not the Scotch tape, because we look at the industry. Another option to improve things is also done in collaboration with TUVN, is to do an high mobility heterostructure where graphene is encapsulated in boron nitride, and to use the split gate to maximize the photo response and put everything in a cavity with a ring cavity where the light matter interaction can be maximized, and so the results can be maximized. Long story short, the mobility is very good in the samples, over 10,000. Remember that already when you got 6,000 or 7,000, the results were very, very good. So 10,000 is really state of the art. And the responsivity is 90 volt per watt, which again is the state of the art when these results were achieved. So if we compare the silicon photonics with the graphene photonics devices, or graphene plus silicon photonic devices, graphene enables modulators with a smaller footprint, with a much broader band. The switches have no static power consumption. So as I mentioned before, the consumption is only when you change from 0 to 1, not when you're fixed at 1 or fixed at 0. While in the case of the silicon photonic devices, there is always power consumption in the static case and also in the transition. And the detectors, graphene is directly broadband, while for silicon, it requires germanium and silicon, and epitaxy has a narrow band. So this, as a consequence, we can get over 10 times reduction in power consumption, in heat dissipation, in footprint, in cost, and so on and so forth. Okay, now we move to the next topic, which is the quantum technologies. So quantum technologies are considered a combination of what is called the first quantum revolution, where collective quantum phenomena were investigated. So we can look at many years ago at the lasers or the transistors. The lasers, coherent phenomena of light, transistors, many electrons working together. And then at the second quantum revolution, where we have individual quantum systems involved, individual electrons, photons, and atoms. However, none of this could happen without a material-based platform. So for the laser, it was the ruby laser. For the transistor, it was originally germanium, then silicon. So nowadays, for the second quantum revolution, we cannot be based on optical tables full of mirrors and things like that. There needs to be integration on chip, which means there needs to be advances in materials. So we need new advanced materials for this to happen. And I'm not just talking about quantum computers. There are many, many things that are possible in these new quantum technologies. For example, the quantum biosensing, examples from QDTI in Harvard, they can do hyperpolarized MRI and map distribution of drugs with high resolution. Or what I'm going to discuss today is the chemometric imaging. So this is first quantum. So it's coherent Raman spectroscopy that can be used to give information, for example, on tumors. So if we go back to graphene is also what is called an ultra-fast Saturab absorber. If we pump graphene not with an ultra-fast pulse, we are now bringing the electrons in the excited state, and before these thermalize or recombine, there is a certain amount of time, not of the order of 100 as here, but probably of the order of 20 femtoseconds. But during those 20 femtoseconds, the next pulse will not be absorbed, which means that I have one pulse in, pulse out, pulse in and out, so it's modulating the light. So this has key application in lasers, because we can use this in order to create ultra-fast lasers that have a broad band of operation. And the whole trick here is to interface graphene with a erbium dope fiber, with a dope fiber, and this can be doped with different dopants. It can be terbium, erbium, thulium, or holmium. And if it's an ytterbium fiber, it will work around 1 micron, and erbium 1 works about 1.5, a thulium 1 works about 2, and holmium 1 works around 3, and so on and so forth. So this is a very simple approach. So we can create a polymer composite, then we can chop down and put into this laser cavity, and then we have an ultra-fast mode lock laser. As you can see here, this is a work done in 2009, already many years ago. The laser, you can see the pulses because this is connected to an oscilloscope. But what is more interesting is the tuning of this intra-cavity bandpass filter, and by doing so, you can see we can have emission across the entire gain bandwidth of the erbium doped fiber. So the limitation is not the graphene, the limitation is the bandwidth of the fiber. So now we are all familiar with spontaneous Raman spectroscopy, so where we use a pump, a laser, and then we look at the incoherent thermal vibrations. But what if we were going to use two lasers, one pump and one Stokes, and the difference of the two would be equal to the frequency of the molecule that you want to see? So this creates a coherent Raman, so coherent molecular vibration driven by the pump and Stokes, and massively increases the signal. So it can create 10 to the 10 enhancement. So if we look at the standard practice of biopsies nowadays, this is based on the histopathology, and the histopathologist looks at biopsies that are stained with dyes, and then the doctor takes the final decision. So the decision is taken on how this looks like. It's not like an objective information in a way, because the doctor looks at the shape, at the color, and so on, and decides that's a tumor and that's an healthy sample. So this creates false negatives and so on and so forth. So what if we were going to use spontaneous Raman for tumor identification? This would work very well. The problem is that it takes forever to take this spectra. So it is slow, and it's not used, cannot be used, for example, in operating theater. So the goal is to create a fast and broadband and coherent Raman microscope. So broadband means high speed and real-time classification of cells. But instead of having an image that is just a picture, now each pixel will have a full chemical signature, and by looking at that chemical signature, we can distinguish the tumor from the normal samples. So in order to do this, we need some laser system for coherent Raman spectroscopy. These do exist, but they are bulky and expensive. So a system like this for coherent Raman, for example, sold by Leica, costs 1 or 1.5 million euros. But besides the costs, they are very large, and they cannot clearly be used in a clinical environment like in a trolley by a nurse. They require specialists. So what if we can do this using graphene? So we designed this system by putting the same piece of graphene in a common leg between two lasers, one working at 1 micron and one at 1.5 micron. So what happened is what you can see in this video. When we switch the laser on, after a little bit of noise, we got mode locking in both systems as expected. But then you see the pulses are perfectly synchronized. So just by putting the same piece of graphene, you can get perfectly synchronized lasers, which is what you need in order to have the pump and the Stokes that you need for mode locking. On the top of for coherent Raman. On the top of it, graphene can operate broadband, and so not only we can work at a single wavelength, we can cover the entire spectrum that we need. So by doing so, we could make this very, very small. This can fit in a shoebox now, and this can actually work. Let's look at some examples. First, we can check some polymer beads and made of polystyrene and PMMA. And of course, they have two different Raman signals, and you can actually tell the difference very easily. But then this is an example of imaging on a tumor, and you can see a standard H&E slide, and on the right, now the label-free SRS, so it's stimulated Raman. It does not require any chemical staining, and you can see the spectra are now plotted as maps, and the maps can be cut at different frequencies, and you can really see the correspondence to the original tissue samples. However, now each pixel is a full spectrum, which means that we can identify in an objective way the chemical composition of each of the points. And this is a major advance. So without spending, so for example, you can tell the bottom part is healthy, the top part is a cancer. I will give you other examples. So this is a multi-channel SRS imaging on a stain sample for a mouse kidney tissue. And again, you can look at the proteins, you can look at the lipids. In fact, what you can do, as you can see now in the next slide, you can actually do a plot where we only plot the lipids, only plot the proteins, or we can plot all of them together. So I have some other examples, but I will just skip them because basically it's the same idea. And just to say that there is a spin-out company that was created called Cambridge Raman Imaging, CRI, and they are now producing this laser for imaging, is already commercial. And in the next few months, there will be the laser attached to the microscope and this system for coherent Raman imaging that can work extremely fast. An entire spectrum can be taken in the sub-millisecond time, microsecond time compared to the standard. So the final point is the use of photons now for quantum information. So why do we want to use photons? Because they're fast, have weak interaction with the environment, via polarization, path information. So if we had a single photon source is emitting a photon at a time, and it's a crucial requirement for several quantum information processing platforms like quantum encryption, quantum communication, quantum computing, and random number generation. However, in order to make this useful, it has to be scalable, it has to be electrically triggered, the operation temperature needs to be as high as possible, as close as possible to room temperature. We require good quantum efficiency, good light extraction, integration in resonator, compatibility with current technology, and so on. So the traditional approaches are, for example, zero-dimensional, they're called atoms, or in three-dimensional, the very successful diamond or nitrogen vacancy in diamond or the quantum dots. And the nitrogen vacancies are great, but the diamond is three-dimensional. So if we add them in a layered materials, they will be at the same side. So single photons in layered materials or layered quantum materials are very useful because they have the ultimate proximity to the interface. So it creates a sensing enhancement and higher emission efficiency. They can be deterministic and scalable sources of single photon emitters, and they can be integrated on chips and to optical circuits. So the whole idea here is to create localized excitons. So we have this valence and conduction bands. There is, for some reason, a localization. So our electron will go there and they recombine on the subbands and they will create single photons. So nowadays, this field that started in 2015 is really exploding, and layered materials are at the core of a huge effort in quantum technologies. Today, if you look in the latest issue of Nature Nanotechnology, we just have a paper that describes all these possible applications and perspective, that discusses the application in quantum communication, quantum networks, quantum computing, single photon detectors, quantum simulation, and quantum sensing. And unlike classical photonics, where graphene plays the key role, in quantum communications, the key role is played by other layered materials. So they by transition metadicalcogenides, or for example, by the hexagonal boron nitride that can work at high temperature, by the heterostructures that can tune the emission, or by what are called the layered Janus material. A Janus material has a different atom at the bottom and the top where you can create a dipole moment and lots of interesting applications. So the roadmaps is to understand these emitters in layered quantum materials, modulate the emission, grow and transfer them in heterostructure scale suitable for wafer scale integration, integrating them in photonic circuits, and demonstration of the LQM-based quantum photonic integrated circuit. So we want to have an integrated circuit where we have the single photon emitter, the single photon processor, and the single photon detector at the end. And this, of course, has many challenges In particular, the single photon detection using graphene-related material is not so advanced at the moment. It has been demonstrated by Effeto and others in Europe or in US. But when it comes to the emission and the modulation, we certainly have a winner there. So this quantum integrated photonic circuit is really the future direction where we want to give. In the final 2 or 3 minutes, I just want to give you some examples. So in 2017, we have created arrays of single photon sources by using pillars and putting TMDs on the top of each pillars. By doing this, just by placing the TMD on the top of the pillar, we were able to get emission in every single site, or 96% of the site were emitting a single photon emitting light. So how do you see single photon emission? You have this broad luminescence. These are the delocalized excitons, and then you have very sharp lines. These sharp lines are an indication of the possible presence of localized excitons. And then you do these anti-bunching measurements, these G2 measurements, and you want them to be as small as possible. So, and these are well below 0.1 or 0.2, which is a pretty decent number, considering that many papers are just publishing with 0.5. So the line widths are very small, 180 microns, microelectron volts, not milli-electron volts, so very, very, very sharp. And as I mentioned, 96% of the pillars that are not pierced are emitting single photons. So this is a single photon emission on a large area. The second point is we need to get them emitted on demand. So we need a switch, and when we switch this on and off, the emission starts or ends. And this was created by creating quantum LEDs when we use graphene, HBN as a insulate, as a tunnel barrier, and then the TMD. And by basically using graphene as the switch, the electrical switch, if we populate the conduction band, then we can have tunneling and emission. If we depopulate, we can stop this. So I'm not going to go into the details because we don't have much time. So let me skip a few slides and let me skip forward. So this works, and the emission was found. So as you can see here, there is a normal LED and a QLED structure, and we do have the single photon emission that was also verified by using the G2 measurements and the saturation intensity. So not only we can emission where we want, we can emission when we want by switching them on and off electrically. And this works in HBN, WS2, and many, many other materials. And that's it. At the moment, I will just stop here. So I want to go to the conclusions and acknowledge all the funding agencies, in particular the ERC, PSRC, the Quantum Flagship, the Graphene Flagship, and all the collaborators that have been working on the different areas that I've discussed today. And if we just look at the quantum application, it's quite amazing to see that the single NV vacancy in diamond is from 1996. Is in 2015 that we have the first detection of emission in TMD, in transition metallic alkylgenides, and already in 2022 there are discussions about integrating HPN emitters with a CubeSat. So even more quickly things have moved on in the quantum field. Okay, thank you very much for your attention.
Thank you very much, Professor Ferrari. It's an amazing and very rich talk. We really, really thank you for gracing us with so much information and such fascinating topic. And so I am going to share my slides again, and I want to first introduce our panel. Alice needs no introduction, is the founder of iCANX and an expert in flexible electronics from Peking University. Welcome, Alice, to the panel. The next person is Dr. Julia Chang. Julia is got his PhD in MSc at Iowa State University in 2020. Then she worked in liquid metal-based fabrication and self-organization of materials, and from that work, she got some wonderful papers, two of which were featured in Langevaartig Chemie and also in Forbes magazine, which was very fascinating. And then Julia is now a postdoc at NCSU, where she's continuing the work on autonomous self-organizing materials. She is very well accomplished in both nanomaterials and fabrication at a macro scale. So Julia, welcome to the panel. And with that, I want us to switch to the panel. And Julia, we're going to give you the first chance to ask questions to Professor Ferrari.
Sure. Thank you, Marty, for the introduction. And thank you very much, Professor Ferrari. You showed us a lot of cool potential applications of graphene materials during your talk. So my first question is toward the graphene ink produced by white exfoliation. I assume that the ink is a mixture of graphene and a solvent. So what is the effect of solvent on the property of graphene? Is the graphene more like in a graphite state rather than single layer in the solvent? And finally, what is the mechanical property of this ink, especially for the aerospace applications you showed in the talk? Thank you.
So as mentioned, the inks started in 2008. So now it's 2023. So a lot has been done in this year. So essentially we can do everything now. So we can use solvent, but we can also do them in water. I mean, water is still a solvent, but you can exfoliate them in water directly. There are ways to remove the solvent after the ink is produced. You can even produce directly master batches. So you can make graphene polymer composites directly in HPH. So in the high pressure homogenizer, so I have a movie that I didn't show. So you get directly polymer composites. So nowadays, the know-how is such that you can basically do whatever you want, which means you can have an ink that is mostly full of single layers, an ink that is mostly full of big flakes. You can have an ink with different flakes of different dimension. You can tune the lateral dimension and you can tune the vertical dimension, which means that the inks can have all sorts of properties when they are printed. For example, you can print and measure sheet resistance well below 1 ohm per square by using inks. And remember that many years ago, the sheet resistance was giga ohm per square when we first did this printing. So it's all down to chemistry, functionalization, thermal treatments, all sorts of treatments that people have learned how to do over the years. So nowadays, really, it's basically what you want to do, almost everything you want to achieve, it is possible. Of course, if you want an ink with only single layers, all of them 10 microns, it takes a lot of effort and the yield is extremely small. If you can live with a ink that has a distribution of sizes, both in terms of lateral and vertical size, is much easier to do, much higher yield, much less work, and this is what is mostly used nowadays in application. In terms of mechanical properties, when you put the graphene ink or the graphene into polymers, with a few percent of graphene, maybe 1%, you can get 10, 20, 30% increase in Young modulus and so on. So there is a huge improvement that you can achieve with a small amount of material. And that is why it is very favorable, especially for aerospace application, because you can save weight by not, you can basically have the same mechanical properties, but lower weight of the components. And that can also be very useful. And again, such a huge amount of work has been done in this area in the past few years that there are all sorts of examples around. So for each example, you can write an entire paper, so give a talk of 1 hour speaking about one particular example, how the ink was done, what chemistry was used, what functionalization was used. So there is a huge amount of know-how there.
Thank you so much. And my second question, as a learner of graphene materials, I try to go into the science area a bit. And a lot of fascinating properties of graphene come from direct points exist in its band structure. Detaching band edges eliminate band gap, while also enabling ultra-wide bandwidth optical behaviors of graphene. However, in my view, like direct points can be a double-edged blade. Maybe it can be a beautiful servant of charge transport, while a dangerous master of like stable states, especially when combined with phonons. And the semi-metal feature of graphene seems to be more frequently applied than its semiconductor features. So my second question is, except the poly exclusion you mentioned a bit, like in the talk that could be achieved by doping, is there any other method to explore the semiconductor features of graphene in the field, Professor?
Okay, first I have to say that I really don't like when people say semiconductor feature in graphene, because graphene is everything but is not a semiconductor. I know that is I have Dirac point, which is good and bad, and everything that is good and everything that is bad about graphene comes from the Dirac point. So I have not shown you any single application in transistors or any of these, not because they don't exist, but because the Dirac point creates a significant problem. You cannot switch off the devices and so on. And then you need to do other kind of devices, very, very interesting devices with a little bit complicated architecture that we are not going, I didn't cover, I didn't want to discuss today. And then if you go towards semiconductors, you really need to go to real semiconductors like transition metal dichalcogenides. And if you go in the roadmap, the electronic devices and system roadmap for 2028, 2030, the nanosheets indication, the roadmap of IMEC and so on, is quite clear that for the development of the Moore's law, we need to use real semiconductors like TMDs, and they do have all the potential, but still we don't know if they're going to be successful. On the other hand, I spent a lot of time speaking about optics, because the optics of graphene is beautiful, is exceptional, is unique, it's easy, and it all boils down to the Dirac point. And that is optoelectronics, it's the key. So graphene very easily allows you to do modulators, mod-lock lasers, photodetectors, all sorts of devices that are more broadband than any other material, less energy consumption, quicker. All sorts of properties are much better due to this particular band structure. And so, yes, then you may need to dope or change the Fermi energy, do other things with it, but this is really truly unique. I then switched, in the case of quantum application, mostly to the TMDs or HBN, because we need to exploit excitons, and we don't really have good excitons in graphene because of the Dirac point. So we do need a band gap. So if we need a band gap, let's go to a material with a band gap. And then again, there are a lot of extremely exciting applications that you can have in the quantum field by using the TMDs and HBN.
Sure, because I read some papers like showing the coloring of the graphene, and some of it might be like generated by the defects in the structure. So is this like plausible, like to become a kind of a stable property for graphene? Or you prefer like graphene should be used as a semi-metal more to be applied as a transparent conductor and have its own like applications?
So it was in 2009 or 8 that we showed that the emission of graphene can be tuned with defects, and you can have different colors and so on. And then many, many beautiful papers have been published afterwards. I also wrote a news and views, I think, in Nature Photonics last year on this. But frankly speaking, if you want my personal opinion, as interesting, actually, I'm now writing another paper on this multicolor centers in graphene. But it's interesting to write some papers, but I'm not super excited in terms of final application. If I look at the mass application for everybody, everywhere, the ones I mentioned in the optical communication and in quantum, at the moment really means today, maybe tomorrow something happens and I change my mind, but at the moment, these are the most exciting. And then everything else is beautiful, and that's the beauty of graphene. You can do a lot of things. Think about the double A of graphene, the beautiful work of Pablo Jarillo on the twisted samples and Alan McDonald and so on. There is so much to be still done and discovered, but I look at the very practical application. I mean, if you remember many years ago, I think it was already 2004 or 5, people were talking about graphenium, as a mocking of Intel inside, that it was like going to displace transistors with graphene devices. It's not going to happen. But in the area where it is bound to happen is the area of optical communications. And is an area where, unlike composites, unlike many other examples I've shown, you use the Dirac cone to your advantage, which is also interesting because at the end of the day, the Nobel Prize is for the Dirac cone, not for the Scotch tape.
Sure, thank you. And I got one last question. It's like from your bio, we know that you are the founder and the director of several famous graphene technology centers in Europe. So we are very curious about the driving force that make you decide to devote yourself in investigating this magic material. So could you tell us about some stories behind it?
The driving force. I think the story is very simple. I was working in, as many other people were, in carbon nanotubes, and before nanotubes in amorphous carbon. But then I was in particular interested on Raman spectroscopy. And what was interesting about Raman is that to understand the defect, the D peak in any carbon materials, it turns out that the D peak is related to the edge of the Brillouin zone, that is the point where the Dirac cone is existing. So already in 2002, 2003, myself and many other people were all looking at this problem. And it was amazing that people have been studying nanotubes and so on for years, and nobody studied the flat material, which you roll up in order to make the nanotubes. And that's how already in 2004, we, together with Maui and other people, we published this paper on the cone anomalies in graphene that was basically out a couple of months after the first paper from Manchester. So for me, it was about understanding vibrations in every carbon materials, in particular the D peak. Actually, the D peak in the Raman spectrum of graphene is a very fascinating feature that goes at the very core of all the Dirac physics in these samples. And it tells a lot of interesting things related to everything else. So that is my initial driver. More recently, and strangely enough, when we wrote the proposals for these large centers that you mentioned, the graphene flagship and so on, is like when you write a proposal, normally you say, okay, maybe this new material can apply for this and that. And what happened over the years is that thanks to this large investment of the EC, a lot of ideas that we thought, okay, it's just a nice idea to have become reality. So what has been surprising is to see how the material has developed from really a complete sort of strange material for scientists in a lab that gets the Nobel Prize to a real serious material for applications. And now I'm in contact with most, if not all, the key European industries working on graphene. We are actually launching officially in a few weeks an industry consortium, pan-European industry consortium of all the key players in the area. And we are actually now discussing with the EC about some other large initiatives that will probably be announced in the next few months. It is nice, you do nanotubes now, then you do perovskite the next day, then you do quantum dot the other day, you keep publishing papers, but it's kind of boring in the end. What is exciting is to actually bring the material from the start to the final application. And that's what excites me now, much more about the Dirac point. It was really exciting. I was excited about the Dirac point in 2003. Now I'm excited about industrial application.
Thank you so much. That's very helpful. That's all my questions. Thank you.
Okay.
Thank you very much, Julia. Alice, do you have questions?
Yes, yeah, I like the talk very much. Actually, I learn a lot from that. Yeah, I'm really excited for the graphene already go to the space. Even landing on the moon. That's very very super. So as Andrew mentioned that even material. Finally, you're not inventing the uninvented the material. Also use it to get massive production. That will be very nice. So I think the idea for graphene plus silicon photonics, that's a very super idea. So you use that double single layer graphene for all these kind of structures. I mean, you did a lot with this like silicon nitride, all this silicon family materials to make the structure. Did you deal with other structure, other materials, for this double single layer graphene structure?
So there are, of course, many other materials and other technologies. We are studying the interaction with 3,5s and other kind of substrate. We are studying, of course, the interaction with silicon nitride. There are other material platforms not made of silicon that are actually quite interesting for integration, and all of this is going on at the moment. And of course, especially for quantum, now the focus is on large area growth of BN, boron nitride. We have a paper coming out soon where we show that we can grow up to 8-inch of boron nitride with a quality that is very similar to the one that is being exfoliated. So extremely high quality material, specifically for applications in communication and quantum. So as you know, there's been almost 5,000 layered materials identified theoretically, exfoliated only very few, maybe 20, and heterostructures even less. And then think about the opportunities. Just 2 layers of graphene. According to the angle, we have a superconductor, semiconductor, insulator, and so on. And then when you put all the other TMDs together, and then you twist them, and then you change the number of layers. So we are almost infinite amount of possibility, most of them not explored yet. So there is so much to do in all the other materials. On the other hand, there is a point where progressing a technology requires focus. And for this reason, we now focus on the double single layer, on silicon insulator, on silicon nitride. And also just even, the transistor was invented in 1947. In 2023, Samsung is investing ginormous amount on the transistor to do the 3 nanometer, 2 nanometer node. So it's the same device that was invented in 1947. So my statement for everybody that is listening to us, that oftentimes as scientists, we like to jump ship. We jump ship even before anything happens, okay? We just want to keep doing something new. And a lot of papers, they show some new things that are almost some gimmicks that, of course, you can doing them in the lab and it's fancy, but will this ever be able to be transformed at a large scale? For me, 2023 and the next 10 years is the era of integration on wafer scale. All the fancy materials that you made, you need to integrate on the wafer scale, not on the 1 nanometer high resolution TEM square. Make a big wafers. And I'm telling you, I'm pleased to see that most of the journals, including the big journals, are now sensitive to this. You do a big wafer scale integration, you can get in Nature and Science and everywhere else, while maybe a few years ago you were not able to get. And it's fun, and you need to use the brain. It's not something that is like, oh, okay, it's the same thing, and we just need to do a new completely crazy material. Who cares about borofin? I mean, with all due respect, yes, there are all sorts of fancy materials out there, but we also need to be able to do them on the wafer scale.
Okay, yes, I like that word. So that's my second, following questions. I mean, maybe you need to, can put some efforts on to do like a simulation tools or even some fabrication, tools going together. So I saw you already announced for a layer level fabrication foundry, right? Yeah. If you want get more people can use this foundry to follow out to make a structure, maybe this is necessary.
So we have two foundries at the experimental pilot line level. One is the European experimental pilot line that we started as a graphene flagship, and the other one is Layer Material Research Foundry. It started in the UK. The next step is to actually do the real pilot, and in terms of the the challenges is the what I mentioned before. So we need to go to the larger scale, go out from the research foundry to the pilot foundry, then to the full foundry. And luckily in the US and the EU, they are the CHIPS Act. The UK is the UK semiconductor strategy. Stay tuned, expect that there will be investments in this area later on. All these facilities are open to everybody everywhere, so you can go and access the experimental pilot line from everywhere in the world, and you will be able to access Layered Material Research Foundry when it's open from everywhere, not just in the UK, everywhere in the world. And of course, the design tools are being designed, but luckily, already COMSOL, Lumerical, and so on have some modules that if you know how to use them properly, they are good enough to do most of the design tools for the samples that we need to work with.
Oh, that's very nice. Actually, I'm thinking if you have already done some tools can be combined with this popular, kind of models, so that's quite easy for we training students. Yeah, we got them, to do some new trial. Yeah, thank you very much. That's very nice. Okay, Martin. Yeah, that's my questions.
Thank you very much, everyone. Andrea, I cannot tell you how much I appreciate this talk. It's fascinating, and even more important, the philosophy that you're sharing with everybody. The idea that you first need to think and stick with something, don't rush for popularity. And my question to you is, because I feel I'm in the same spot. I try to think of science as a feed to the industrial complex. You take the science and translate it and make something useful. And more importantly, think, don't rely on a tool. And especially on these high-end material, we see a lot of people who become experts in using very sophisticated tools, and they over-characterize the material, and they make those little coupons, and they spend all their life trying to generate more and more information, which eventually can be good, but they will never ever move the material to application. So my question for you is, as we train students in postdocs and at all different levels, how do we incorporate this level kind of thinking into their training? It's easier with graduate students and postdocs, but with undergraduate, how do we even start bringing them to realize that you need tenacity, you need the grit, you need to stick to something, you need to avoid looking for whatever the shining next to it, and find a solution. Use your brain to bring a solution to the table. So how do we train students to do that?
I think it's a difficult question. It also depends on the countries. Unfortunately, some countries, they put some pressure on the supervisors because they have a reward system based on impact factor of the papers and so on, instead of actually real advance. Unfortunately, wafer scale and so on requires a lot of work before you get a result. I've learned from colleagues doing space. Think about these people from the rover. They spend 4 years and then the rover crashes. We are kind of an extreme consumerism when it comes to material science or semiconductor physics nowadays. It's like we're like the social media of the science, because we need to do, it's almost like Twitter and something like that. And after the next day, you need to do something new. So this has to stop, but it has to start by example. I have to say that we also need to start teaching, for example, packaging. There's almost no packaging done in university, in what you would consider in Cambridge. We are now considering bringing back maybe potentially a master in packaging, bringing back facilities to do packaging is fundamental. And if you look at more, the chiplets and so on, the trick will all be in the packaging. And we are not teaching that. I mean, Cambridge is not teaching that. I don't know what the other universities do. And this is not done for any other reason. It's because the supervisors, the professors, are bred or have been bred in the past few years with these quick rewards in terms of paper and so on, but not enough reward for innovation. And what I want to stress is that technological development, innovation is not boring. It is hard, it is exciting, it requires a lot of effort, and people need to be transmitted this, but we need to also build in a reward system, an evaluation system for the faculty and so on that takes this into account.
Thank you very much. I can tell you it's the same even in the US. We know the processing, the packaging, all that knowledge is very difficult to come by in campus.
Exactly. And everybody needs people with this know-how, and we are not providing this know-how.
Yep. My final question to you is, you mentioned something about the semantics, the language. For example, people talking about graphene and how they can create a band gap and all these kind of things, and they start using graphene as semiconductor. I'm with you that graphene as a material has that direct point. Forget about it. It doesn't have a band gap. It's not a semiconductor. But for the young students, for the people who are trying to get in the field, they are bombarded by this information of, graphene can do X, this material can do Y. And sometimes, because of the catch-up of getting papers and publications and getting the next YouTube moments, so to speak, the language gets convoluted. How do we then help these young scientists and students understand how to distill that information? How do you help your group, if I can put it this way, get over the mischaracterization of something that is so fundamental and obvious?
I mean, how I help my group is that from time to time I write some perspective and review papers that they seem to be liked by everybody. As I mentioned, today I just have one out in Nature Nano. But what I learned that is we cannot really go back. For example, quantum materials. What does quantum material mean? What is a quantum? I mean, quantum LED and LED. An LED uses quantum physics and quantum technology anyway. There's no. So the only way is to sort of embrace and define. So I'm now planning to write a perspective to explain what is a quantum material and what the definition is. So I'm not going to be saying, okay, that is not possible, we should not use it all the time, because at least try to put a definition and a real definition. So that's why I prefer layered materials to 2D materials, because very few of them are 2D, most of them are multi-layers, so they should not really be called 2D. And in the case of graphene semiconductor, I mean, graphene is not a semiconductor, and then it's super easy to do all sorts of approaches to create a band gap in it. But what's the point? If I have a material that doesn't have a band gap, I mean, I have many materials with a band gap already available. Yes, I can take a semiconductor and make it a metal and vice versa. What's the point? So the point, I mean, yes, you can write a paper, even in Science and Nature, but isn't it better to embrace what the material is and try to find a way of using it to the best without doing these gimmicks? I mean, we can all do these things. We learn quantum confinement almost when we are in high school, so it's not difficult to do it. But clearly, it's not what the material likes to do. Otherwise, it will already be like that. So unless you find something, you need to exploit what is intrinsic in the material, and in some clever way maybe, and get the final application. That's my view. We can always write papers on any topic we want, of course. Sometimes there's a counter argument with respect to what I'm saying. The first paper describing the massless Dirac fermion was published by a Canadian theoretician in 1947. And at that point, nobody cared about this paper. It was in PhysRep B, nobody read it, and so on. And it became very important in 2004. So sometimes, you still need to write papers on weird stuff because we don't have enough nobody has enough know-how to know that this paper in 20, 30, 40 years' time will be very important for something else. So we always need to embrace that. But we also need to not lose the focus and going in every direction.
Very good. So with that, I think I want to thank you very much for your talk. I wish we had more time. We really enjoyed the way you think, the way you approach these materials, and the enormous amount of knowledge that you hold. So we hope we'll be privileged again to have you at some other point to engage a little bit more. But for the sake of time, I have to continue, and I want to present these certificates to you for gracing our volume 148. And we thank you very, very much. And it's the reason why we have this platform, is to educate and open people's minds to areas beyond what we can individually do. So thank you very much, Professor Ferrari.
Okay, thank you. Goodbye.
Yep. And with that, I want to inform everyone that we're going to have volume 149 next Friday, where we'll have Professor Brian, who will be talking to us about nanomaterial chemistry, creating a universe in a grain of sand. And with that, I want to thank everyone. Thank you so much. Really appreciate it.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can。